Hi everyone, my name is Minghan Wei. Now I'm going to introduce our work on energy mapping and energy-efficient path planning for agricultural robots. When robots are performing agricultural tasks, autonomous navigation is a basic and crucial functionality since they need to move in fields. In a real world, we have to consider practical constraints for path planning, such as the ground traversability, the motion constraint of robots. Meanwhile, since many robots are now powered by batteries, they have limited energy budgets. Part of our research focuses on how to plan energy-efficient paths under the limited energy budget constraint. We identified two challenges associated with the energy constraint. First, with energy constraint, the robot may not be able to finish the mission with the power of a single battery. They may need to visit a recharging station to get recharged and then continue to work. This challenge calls for new planning algorithms that consider recharging phase for path planning. More specifically, for this challenge, we study coverage path planning problem under the energy constraint. Many applications, such as environmental monitoring, searching, and mapping, require robots to fully cover given environments. With energy constraints, the robot may not be able to completely cover the environment in one iteration. We need to plan multiple paths, and between two paths, the robot visits a recharging station. We formulate this coverage problem as follows. We model the environment as a polygon, and there's a single charging station in the environment. We also know the energy budget of the robot. Our goal is to plan a set of paths and minimize the path number such that when the robot follows each path, the, the, the entire environment is covered, and each path should be within the energy budget. In this problem, we assume the environment is uniform such that the energy consumption is proportional to the moving distance. Since this problem is NP-hard, which means that we cannot find the optimal solution within polynomial time, so we turn to approximation solutions. Here, approximation means that even though we cannot find the optimal solution, we can guarantee that the cost of our solution is within an upper bound of the optimal cost. Our first approximation algorithm has a constant approximation rate, which means alpha equals 4 for contour connecting environments, which are defined in our work. When it's extended to general environment, the approximation rate alpha is the number of reflex vertices. In another word, the performance of our first algorithm is associated with the complexity of the environment shape. Our second algorithm has a log D approximation rate, where D is the first distance from the charging station. So the performance of our second algorithm is related to the environment size. To validate our solution, we apply our method in experiments to an environmental monitoring application. We would like to use this UAV to take images of every location in this given environment. On the right figure here, we plot the UAV trajectories in this environment. The UAV cannot fully cover the environment with a single path, and the path number here corresponds to the approximation rate we present in the previous slide, which validates our solution. Now let's look at the second challenge associated with the energy constraint, the lack of energy cost maps. Existing planning algorithms require environmental maps for path planning. However, the energy consumption profile of ground robots can be very complex in fields. So it is not sufficiently addressed that how to efficiently obtain energy cost maps for energy-efficient path planning. For this challenge, we take data-driven approaches and using learning-based methods to build energy cost maps for energy-efficient path planning. We use both aerial vehicles and ground vehicles for data collection. We use aerial vehicles because they can efficiently cover large areas to collect ground appearance information, and the ground vehicles can provide actual energy consumption data of the ground robots. Combining these two pieces of information with the deep neural network, we are able to predict the energy cost maps of the entire given area. To show the advantage of using the map built by our method, we compare the paths. In experiments, we compare the shortest Euclidean distance path with the energy-efficient path planned by our map. As we can see from this video, using our map, we can guide the robot to low-cost terrain class to goal locations. Among all the experiments, we see that using our map, the robot can save 10 to 30% of energy depending on the environmental property.